All right, welcome to the fourth section of this chapter. And we're going to continue talking about polynomial functions, and today we're going to talk a little bit more about how we can analyze the graphs of those functions and learn some things about them. So we have already talked a little bit about maximum and minimum and what the graphs of those look like. Today we're going to graph polynomial functions by hand, and we're going to find their zeros. Remember, zeros are the same as x-intercepts. Oops, sorry. And then we're going to find the relative minimum and maximum values of polynomial functions. So we have some new vocabulary you'll have to be focused on today. We'll be defining it throughout the lesson, but it might be a good idea to come back and write a definition for yourself, or just make sure that you know what each of these are so that you can identify them when you hear them in class or in different problems. Okay, so the first thing we're going to focus on is graphing a polynomial function. To graph a polynomial function, you need to make a table of values. Then you use that table of values and you plot the points, and you connect them to make a smooth, continuous curve. Polynomial functions are always continuous. And then this is super important. We're going to use the end behavior to make sure that you have enough points. So for example, if you know that you have an odd degree function, right, and these are the only points that you have, then, and you know that it's an odd function, you know that both ends have to go in opposite directions. So you see this end here going up, you know you should probably plug in some more points until you get the ends going in opposite directions, for example. All right, so let's take a look at this first example. We're going to graph f of x equals negative x cubed minus 4x squared plus 5 by making a table of values. So I would suggest that you pause the video for a second and fill in the table of values that's on your notes, and then compare it with the one I'm about to pop up here. So here we have a bunch of different points. Usually, at least right now, we'll just start by picking some positive and negative numbers and 0 and see if that gets us enough points to plot our graph. So there's the point negative 4, 5, negative 3, negative 4, negative 2, negative 3, and so on. Notice that they're plotting each of these points. There's not space for 2, negative 19 on the graph they have here, so we won't plot that. And then they connect those points with a smooth curve. Let's talk a little bit about the end behavior. Since this is an odd degree function with a negative leading coefficient, I know that f of x, oh, there, I have it on the next part. F of x will go to positive infinity as x goes to negative infinity. So here, as x is going to the left, I know this should be going to positive infinity, which it is. And f of x goes to negative infinity as x goes to the right, as x gets really positive, which it is. And since this is cubic or odd degree, I expect my ends to be going in opposite directions. And then notice that my graph intersects the x-axis at 3 different points. That represents 3 real zeros, or 3 real roots. Okay? So you always want to check your end behavior to make sure you got enough points. So I want you guys to try this one. All right, the answer to this one should be C. All right, here's an example of what your table of values could have looked like. Again, you should have thought about the end behavior of this function. It's a positive leading coefficient with an odd degree. So as x goes to negative infinity, y should go to negative infinity. As x goes to positive infinity, y should go to positive infinity. All right, now we're going to talk about something called the location principle. The location principle is actually very logical, although sometimes we don't necessarily think about it. But it says, suppose that f of x represents a polynomial function. So here on this graph, this green curve represents a polynomial function, and a and b are 2 real numbers. Okay, so here a is some x value, and notice that f of a is a negative value, so that's below the x-axis. And when I plug in b, f of b is above the x-axis, a positive value. So f of a here is negative, and f of b here is positive. That's what it says here. F of a is less than 0, and f of b is greater than 0. The function has at least one real 0 between a and b. Where is the real 0 on this graph? It's right here. The 0 is where it crosses the x-axis. This makes total sense, right? A and b are both positive x values, but we're looking at the y value of the function, right? So if the y value of the function goes from negative, meaning below the x-axis, to positive above the x-axis, it has to cross the x-axis in the middle. Makes sense, right? So where my y value goes from negative to positive, I have to cross the x-axis somewhere between those two x values. I have to have an x-intercept. So let's take a look at an example to see how we would figure this out. Here we have a 4th degree function with a positive leading coefficient. So I will expect both of my n's to go up. Okay, so thinking about n behavior. We're going to make a table of values, which they have for you here. Since f of x is 4th degree, I'm expecting it'll either cross the x-axis 4 times, 2 times, or not at all. So let's take a look here and analyze our y values. Here my y value went from positive to negative. So that means that somewhere between these two x values, there has to be a 0. There's also a change here. It goes from negative on the y to positive on the y. And there's another change here, and another change here. So in this case, I expect 4 real zeros. I expect my function to cross the x-axis between -2 and -1, between -1 and 0, between 0 and 1, and between 2 and 3, based on that location principle. So when we sketch that graph, notice that that's true. Here I have a 0 between -2 and -1. I have another one between -1 and 0. I have another one between 0 and 1. And I have another one between 2 and 3. If you go back and compare to the table of values that you should have written down on your notes, you will see that that's exactly where I expect my zeros to go, because I go from positive above the x-axis, below, above, below, and then above again. And notice that both of my n's are going in the positive direction like we expected. All right, you guys try this one. Making a table of values and determining the values of x where the real zeros are located. Okay, the answer here should have been B, and I'll show you a table of values. All right, here's my table of values. So again, I'm looking at the y values first. So here's a change of sign. It goes from negative to positive. Here's another one. It goes from positive to negative. And then here it goes from negative to positive. Since this is a cubic function, I know the maximum number of zeros, real zeros I can have is 3, and here I have 3. So that means that my actual 0, the actual x-intercept, is between x equals 1 and x equals 0, which is what it says here, between x equals 0 and 1, which it says here, and between x equals 3 and x equals 4, which would happen right here. Okay. Let's take a look and talk about maximum and minimum points. In this graph that you see right here of this blue curve, it's a polynomial function. Obviously, this arrow, right, this function is going to go on forever in that direction and forever in this direction. So there's no absolute maximum or minimum because it goes forever positive and forever negative as far as the y values go. Now, in terms of these bumps in the middle, though, these are called turning points, or points of, well, turning points for now, are also called relative maximum or relative minimum points because they're turning points. So B here is a relative minimum point compared to the points around it. The y values on both sides of B are going to be larger than B. A is a relative maximum because the y values on either side of A will be going down. They'll be lower than A. So B is the lowest point in that area, and A is the highest point in that area nearby. These are called extrema, or extreme points. This is the relative minimum again, and the relative maximum, right? My function is decreasing until it gets to B, then it turns around and starts increasing, then it turns around and starts decreasing again. That's why B is a minimum, and A is a relative maximum. Again, we often call these turning points, so notice this is important. The graph of a polynomial function of degree n has at most n minus 1 turning points. So that means if I have a function that's 4th degree, it could have up to 3 turning points. It might not have 3 turning points, but it can have up to 3 turning points. Some functions, like f of x equals x cubed, it looks something like this. doesn't really have a turning point like these. It doesn't have a minimum or maximum. It just kind of gets flat in the middle and then continues in the same direction. So let's take a look at example 3. We're going to make this graph, and we're going to estimate the x-coordinates where the relative maxima and relative minima occur. So we're going to use the same strategy of making a table of values. So here they have the table of values that you can fill in on your notes. And let's analyze a little bit what we would see here about zeros and relative minimum and maximum. So right here we notice a sign change. Y goes from negative to positive. That's what we talked about in the last example. So I expect there to be a 0 or an x-intercept between x equals -2 and x equals -1. Now let's analyze the rest of our y values. Notice that here I have a 5, and on both sides the 1 and the 3 are lower than 5. So if I was thinking about what that would look like, it would look something like this, right? I'd go from 1 up to 5 and then down to 3. So this indicates it's probably a relative maximum, or that there's a relative maximum nearby. If I look at the 1 here, this is the lowest y value, and the value on both sides, the 3 and the 5, are both larger than the 1. So if I thought about this as being 1, I'd be coming from 3 on the left, then I'd hit 1, and then I'd go up to 5. So it indicates that at this point, 2, 1, 1 is probably a relative minimum, or at least there's a relative minimum close by. So this is just a study tip from the book. A polynomial with a degree greater than 3 can have more than one relative maximum or minimum, right? Because I could wiggle around a bunch of times in the middle before I keep going, and each one of these points would be a relative maximum or a relative minimum point. Okay, so if we graph this, you can see that it actually does work. At the point 0, 5, that's a relative maximum. All of the y values around that point are lower than 5. And we can see that there is a relative minimum at x equals 2, or at least near there. And the 0 is between -1 and -2, just like we expected. That's where it crosses the x-axis. So just so you know, in this example, the maximum and the minimum actually occurred at nice integer points. But that won't necessarily always happen. It could be that maybe this graph would have gone up a little bit more before it kept coming down, and maybe the actual maximum value would be like 5.1 or 5.3 repeating or something like that. So they won't always be at integer values, but the table of values gives you at least an idea of where those points will be. So with that in mind, I want you guys to try this one. All right, your answer here should be A. There's a relative minimum at x equals 0 and a relative maximum at x equals -2. And here's an example of what your table of values might look like. At x equals 0, we can see that the y value there is 2, and notice the y values on both sides are larger than that, so we expect a relative minimum there at x equals 0, because it's asking for the x values. And at x equals -2, 6, both of the y values on either side of 6 are lower than 6, so we expect a relative maximum there. And you might be saying, well, but at 2 and at 3 the numbers got bigger. Yeah, but I'm looking at the numbers on both sides. What this shows me, 6, 22, 56, is that my function is just going up and it's increasing. It's not turning around. What this shows me, like let's look at the -2, 6. The y value on the left was 2, so it went from y equals 2 up to y equals 6. And then down to y equals 4 and y equals 2, and then turned back around and went up to y equals 6. So you have to think about what the actual behavior of the graph is. You have to look at the y values on both sides. All right, let's take a look at this last example. Here we have a polynomial function that's modeling the weight of a patient during a 7-week illness. So we're going to make a table of values for weeks 0 through 7, and we're going to graph just like we did in the previous examples. So there's our table of values. Obviously with this you should be using a calculator to get your decimal values. And so when you graph, here are what your points look like of weeks 0 through 7. So our polynomial function looks a little bit like this. We don't need to graph the part to the left of 0 because you can't be sick for negative weeks. All right, then in part B it says describe the turning points and its end behavior. Looks like there's a relative minimum at week 4, which means that their weight was the lowest at week 4. The trends suggested would be that the patient was losing weight until week 4 and then started to gain weight and is continuing to do so, but we would not assume that that would happen infinitely.